This is Jack Jackson. Let's look at a interesting thing about circles, something called an inscribed angle. Um, so here we have an inscribed angle, and you may recall from our definitions that this is a an angle whose vertex is on the circle, and then the other sides either intersect the circle, or it could be actually can't quite get it there, but tangent to the circle, like that. This is a circle. Here's the center. And the radius is controlled by this point on the circle. And we have an inscribed angle. Notice that it intercepts a single arc of the circle over here, arc BD. So what we have is we have rays AB and AD, and the intercepted arc there. I've got a point in the middle, F. This is actually the midpoint of that arc, and that is arc then BFD. Okay. So how do we measure an arc? Well, we measure an arc by measuring a central angle. Okay, this is at least part of the central angle here. Of course, the angle would actually be two rays. Here we have two line segments that are radial line segments there, and we see that that's 0.64 radians at the moment, whereas this one down here is 0.32. Do you see a relationship there? Well, hopefully you notice that this one for the central angle is twice the size of the intercepted or the inscribed angle, or the inscribed angle has half the measure of the central angle, so that's going to be half the measure of this arc. Let's see if that works here. Well, if you look, if we move this around, it's staying the same. If we change, what happens if we change it here? For example, 0.66, you double that, that would be 1.32. Yeah, that's working out, right? So if you try some different ones, we can see what happens. 1.48, double it, that's 2.96. Yep, that does work out. So it looks like the measure of the inscribed angle is 1/2 the measure of that intercepted arc. Now let's actually prove that. The first case we want to look at, we're going to break this down into cases, and it's going to be easiest if the easiest case is if one of the sides of our inscribed angle goes through the center of the circle. So let's see if we can make that happen here in the picture. That's at least approximately correct there. Okay, now let's look at this picture and see what we have here. Well, what do we have to work with? Well, we've got a triangle here. We know lots of things about triangles. Is there anything you can tell me about that particular triangle? Well, remember this is a circle after all. So these radial segments here and down here from C to A and from C to D are congruent. So that's an isosceles triangle. So that means that this other angle up here is going to be congruent to this one down here. In other words, the angle at D, that is ADC, is congruent to this angle down here at A, that is DAC. Okay, well, what's that got to do with anything? Well, what's that got to do with this red angle here, the central angle? That's the angle DCE, or DCB. E and B are the same point at the moment. Well, it looks like what we have is that angle is going to be the same as these two added up. This measure of this angle is going to be equal to the sum of the two measures of these angles. Looks like right now that's a right angle. Okay, what if we change it? It doesn't have to always be a right angle, but it does have to always be twice the size of this angle A, because why? Because of this isosceles triangle makes these two angles the same size, and this angle right here is an exterior angle to the triangle, and in Euclidean geometry, the exterior angle of a triangle is equal to the sum of the two measures of the two remote angles. Comes from the fact that it's supplementary to this interior angle C for the triangle, and the fact that the angles add up to pi radians or 180 degrees. So we've proved that this works in the case where it goes through the middle. Now there's only, so the point C, if the C is on one of the sides, then we've proved that this works. Now what if C is not on one of the sides of the angle? It's not on the angle itself. Then it's either in the interior of the angle or it's in the exterior. So let's take a look here where it's in the interior first. So draw this diametric chord or the ray AC and let its point of intersection over here be point E. Now, if you look, we could break this down here into two arcs and this into two angles. Okay, so we have two adjacent angles and two corresponding adjacent arcs. Okay, so let me go ahead and create that other arc for us. So the other arc we're talking about is the arc that goes right here. So let's give it a different. Yeah, that's the one I want. Maybe make it a different color. Who knows? Maybe we'll make it green, let's say. So now we see that the green and the red arc measures add together to get this, because these are adjacent angles here for the central angles. So the angles add up here with the angle measure theorem. The angles add up here too. Their measures add up, actually. We don't actually measure, add angles the way I'm doing in my class at least. We add their measures though, we can do that. And so we see here that for angle DAE, we can just apply the result that we had from case 1, where the angle, so for that one, this ray right here, AC, if we extend it on out to a ray, A to C to E and on out forever, that angle that you get for DAC, or DAE, same angle, it fits the criteria that we had in case 1, so that angle from DA to E is going to be half the measure of this green arc here. Similarly, we have the same thing here on this one here. Angle BAE fits the criteria for case 1, and so its measure is half the measure of this red arc. And of course, then if we want to find the measure of angle A, we just add these two angles together, add their two measures together, and we add the two measures together here, which is the same as adding these two arc measures. And so once again, since each one of these is half, since this angle from DAE is half of the green arc here measure, and the measure of from EA to B is half of the red arc measure from B to E, then the total sum here is half of the arc length there. Not arc length, arc measure. Okay, so that's case 2. Case 3 is when the C is on the outside of in the exterior of the angle, like that, for example. Well, it's basically just like the last one. Again, go ahead and draw in this ray going through endpoint A, going through C, hits E up here. Once again, apply case 1 to the angle DAB and BAE, but this time, instead of adding the two angles, we're going to subtract, because this time B is in the interior. A ray AB is in the interior of the angle DAE, right, instead of the exterior. So the angles add up this way. The measure of angle DAB plus the measure of angle DAE is the measure of angle DAE. So if you want to find angle DAB or BAD, this angle, the one we started with, you're going to have to take the bigger angle, right, and then subtract the angle, the smaller one here. So you're going to take angle DAE, take that measure of that angle, and subtract the measure of angle BAE. Well, you just do the same thing with the arcs because you got the same relationship among the central angles here. That since the ray CB is going to be in the interior of the angle DCE, we can find angle DCB by subtracting the angle measure DCE, subtract the angle from BCE. So in other words, basically what you're going to do to find the arc length here, you find the arc length over here to where the diameter will come across, diametric chord there, and then subtract this extra part here. Well, both of those, once again, satisfy case 1. So the big arc across here from D to E is going to be half of the angle from the other way around, DAE, that angle measure is half the measure of the arc from D to E. And then we subtract the arc measure from B to E, which is twice the measure of the angle from B to A to E. Okay, and that leaves this what's left here, the inscribed one, to be half of the other one. Okay. So in the end, we get no matter what, whether it goes through the center or not, we get the measure of the um, intercept. The inscribed angle is 1/2 the measure of the arc that it intercepts. One of the consequences of this is if you have two angles that intercept the same arc, each one of those has half the measure of that arc. So they are going to be congruent, which you see here in the picture. And it really doesn't matter where we place this thing. It always stays congruent to here as long as it's intercepting the same arc. All right, so here's the we can see right here, here's the actual write-up of the theorem for inscribed angles. Inscribed angle theorem. Here's the proof. I'm not going to go, I've already gone over this. I'm just going to leave this on the screen for a second. If you want to pause it and read it, you can. Hopefully there are no typos in this. So here's the proof. We set up case 1. WLOG is without loss of generality. And we can look at that case there. There it's illustrated. And then for case 2 and 3, we're going to put this diametric, this ray that goes through the center of the circle, and we have that set up. And then here's your adding or subtracting angles and arcs. Use the distributive property there to factor its 1 point. Okay, and so we can get this true no matter what. So there's our inscribed angle theorem. The inscribed angle theorem is an important basic tool that we can use to prove several other results, including a couple of corollaries here. We've already looked at this first one. Two angles inscribed in the same circle and intercepting the same arc have to be congruent. An angle inscribed in a circle that intercepts a semicircle is a right angle because the intercepted arc has a measure of pi radians or 180 degrees. Congruent angles inscribed in the same or congruent circles will turn out to intercept congruent arcs. That's the converse of that. That's also true as well. So this inscribed angle theorem turns out to be a pretty useful result for doing other things when we're working with circles.